Today we'll be discussing about Poisson distribution and the Poisson approximation for a binomial distribution. Before the approximation, let's first see what a Poisson distribution is. Suppose x is a discrete random variable with the probability mass function given by p of x is equal to k is equal to e raised to minus lambda lambda raised to k by k factorial. Then x is said to follow a Poisson distribution with parameter lambda. Now let's check if this is a valid PDF. For that, let us take the summation of k is equal to 0 to infinity p of x is equal to k. Ideally, we should prove this as 1. Then this is a valid PDF. So when we take the summation, let's substitute this here. So we'll get the summation of e raised to minus lambda lambda raised to k by k factorial. Let's just take this e raised to minus lambda out. So it becomes like this: e raised to minus lambda into summation of lambda raised to k by k factorial. Now we know that this term will become e raised to lambda. So we'll be getting e raised to minus lambda into e raised to lambda, which becomes 1. So we have just checked it is a valid PDF. Now coming to our main topic, that is approximation of Poisson approximation for a binomial distribution. Say for example, we have a binomial distribution and we have a random variable with binomial, and when we have a fixed p and when n is very large, we know that this case we can actually use a normal approximation. There can be another case when n is very large but p is very small. Say for example p is 0. Then we can't use normal approximation, because in this case np should be very much greater than 1. npq will be very much greater than 1 when you are considering these conditions. So when p is equal to 0, this condition totally fails. So we have to have a different approximation. There we'll be using Poisson approximation. So that's how we have Poisson theorem. Poisson theorem states that if n tends to infinity and p tends to 0 such that np tends to a fixed value lambda, then our binomial distribution like this, which is the standard form for binomial, can be replaced by a Poisson distribution with parameter lambda as np. So this is our Poisson theorem. We can actually prove this. It is little complicated but can be proven. See, let's start with a binomial distribution. This is the form for binomial. Now I'm just expanding this ncx factor, that is n into n minus 1 into n minus 2, which will go up to n minus x plus 1 divided by x factorial. Now earlier I have told for this approximation we'll take np is equal to lambda. From that we can take p is equal to lambda by n. So I can take this p as lambda by n, and q, as we all know, it is 1 minus p. So again 1 minus p, again I can put lambda by n raised to n minus x. So I hope this is clear. NCX I'm replacing with this, p I'm replacing with lambda by n, q by 1 minus lambda by n. From here, suppose if I take 1 n from each of these terms, so I'll take out 1 n from this, 1 from this, 1 from this. So finally I'll have n raised to x into 1 minus 1 by n, 1 minus 2 by n, etc. 1 minus x minus 1 by n. I can just write this as lambda raised to x by n raised to x. I can write this as 1 minus lambda raised to n by raised to n by 1 minus lambda by n raised to x, because this is raised to n minus x. I'm just splitting this. Oh, I'm sorry, this is n raised to x. So here I can just cut these two terms, n raised to x and n raised to x. Also here, when I take the conditions n tends to infinity, this terms, when limit n tends to infinity, when I consider this term will be 0 to this term 0, 0, 0. So ultimately I'll get 1 minus 0, 1 minus 0, all 1 minus 0. So all these things, this will also become 1. So all the entire term will become 1. The denominator will become 1. This is also, I can write limit n tends to infinity, 1 minus lambda by n raised to n will be e raised to minus lambda. So this term will become e raised to minus lambda. So ultimately I'll get lambda raised to x, oh I forgot by the denominator, x factorial. Lambda raised to x by x factorial into this term I am replacing with e raised to minus lambda. This is what? This is, as we have seen earlier, this is Poisson form. So finally, when we have considered binomial, and when n tends to infinity and np is a fixed value lambda, we can approximate the binomial to Poisson. This is the proof for that. So this comes in very handy when we do a lot of problems with large values of n and small values of p. We'll just quickly see one example. Let's consider an order of 3000 parts, of which some may be defective. Let's say probability that a part is defective is 10 raised to minus 3. So that gives n is equal to 3000 and p is equal to 10 raised to minus 3. Now we have to question is find probability of k is greater than 5. That would be what is the probability that there will be more than 5 defective parts. So we can just find probability of k greater than 5 is equal to 1 minus probability of k less than or equal to 5. Say for example we are putting binomial. We have to write 1 minus summation of n c k p raised to k q raised to n minus k. K is equal to 0 to 5. And if you see here, actually our n is 3000 and p is 10 raised to minus 3. So solving this with a binomial would be very difficult. So this is where our Poisson approximation becomes helpful. We can actually replace this we can actually approximate to a Poisson distribution like this. E raised to minus lambda, lambda raised to k by k factorial, which will become 1 minus e raised to minus lambda. I can just take out sigma k is equal to 0 to 5 lambda raised to k by k factorial. What we see is this is way simpler than solving this. So that is where we have that is where we use the Poisson approximation.